sort of normal length test would be 28 questions on it, same as the other tests that we've had. Capacitors, capacitor circuits, capacitors in series and parallel and in combination circuits. And then we have resistance. Let's write it down. So we capacitance, capacitors in series and parallel. And then also in combination, the energy of capacitors. Then we have power, current, Ohm's law, resistance and resistivity. So how do we calculate the resistance based on the physical properties of a material? I'm going to put resistivity. I'll just put a row. Resistivity. And then moving into DC circuits, the idea of EMF and terminal voltage. EMF, terminal voltage. That's the internal resistance in the batteries. That's really just an application of Ohm's law. Resistors in series, parallel, and combination. That's it, right? I miss any topics? I think that's it. Yeah, that's all. So we can go over a test if you like. Are there particular questions that y'all want to review though before we do that? Kristen? Oh, I'm sorry. Bree, we'll get you next. Okay.
When it comes to you had two questions right next to each other. One was asking for the potential across, and then the other one was asking for the difference in potential across.
Okay, those are the same things.
Are they?
Yes. Can you direct me to a question on those?
It was
The
29 and 30.
29 and 30.
29 and 30 and 31.
Oh yeah, I see. Yeah, it's the same. So right here we have difference, and then over here we just have potential. When I say potential across, it means what is the potential, across this capacitor, between those 2 points on the capacitor. So whenever I'm talking about the potential on an electronic device, it's always the potential difference between 2 points. I see what you mean. I'm sorry if that confuses you. Yeah, we get a little loose in circuits because it's always potential difference. We're never talking about the potential at a particular point in a circuit.
So, one more question. For number 29, I got 1.2 and I see how I got it. But for 31, when I did it, I was a little confused because the answer is 18, so you got 36 and you split it in half.
Right.
Because it's a series, right?
Right.
So if 29 is in series, how come you didn't split the 1.2 amongst all of them?
Okay, so 31 is split evenly. We have 18 volts and 18 volts here, but only because these two capacitors are identical to one another. But over here, these are all different. Right, so like if we wanted to find the actual charge, like doing it the long way, or finding the voltage the long way, let's do it with this one first. First, I'd find the equivalent, which is 1 over 8 plus 1 over 8. That's equal to 4, right? 2 8s, 1 4. Yeah, that's 4. And then so that is a circuit that's 36 volts, 4 microfarads. And so that tells me that Q is CV, so 4 times 36, that's 144 microcoulombs. So I have 144 on both of these microcoulombs. Have I lost? Am I going too fast? You clear? Okay, and so then if I want to know the voltage, it's Q divided by C. 144 divided by 8 is 18. And because they're both the same, these are both 8. They're both 144 divided by 8. Whereas over here, let's see, what was the equivalent of this? The 3, 6, 12, and 24. Okay, yeah, so over here it's different. I have the equivalent is 1.6 microfarads. Well, I say it's different. It's the same procedure. Then the charge on that is 1.6 microfarads times 18 volts. And then that charge Q is on every one of these capacitors. And then if you want to know the voltage across any one of these, the voltage is Q divided by C. So you'd say that charge divided by 3 for the 3 microfarad. And so you have different capacitances, so you get different voltages. That's right. It's a lot easier when they're the same because then you can just split the voltages up. And you'll encounter some problems like that, but you'll also encounter problems where they're different capacitors or different resistances too, because you do the same procedure with resistors, except here where we found the equivalent capacitance, you'd find the equivalent resistance. And then here, instead of finding the equivalent charge, you'd find the overall current. Right? And then you would apply that current to each individual resistor. It's the same procedure though, except just you're dealing with current instead of charge. Bree?
On exam 2 first.
All right.
Number 16 and number 27.
Okay. 16, you say?
Yeah, I think it was just a matter of like, because I got 2 instead of 200, I think I got like 0.2 or something.
Let's take a look. Maybe there's a mistake, but I don't think there is. So first of all, you have to find the capacitance. There is no dielectric constant. It's 1. So I'm just going to leave that out. Epsilon naught A over D. 8.85 times 10 to the minus 12. That's farads per meter. And then the area is 0.2 meters squared divided by 0.0001 meters. And so that'll give us our capacitance. I get 1.77 times 10 to the minus 8. That's in farads. And then if I want to know the potential, Q is equal to CV, so V is equal to Q divided by C. Oh, I see. I better know what you did. Here we have to convert this to coulombs. Did you do that? Yeah, that's your problem. And then 1.77 times 10 to the minus 8 farads. That gives me my voltage. I get 225 volts or 200 volts, rounding off to 1/6. All right. So that was the problem. You didn't convert your coulombs, your microcoulombs to coulombs. You never go wrong with SI units. Sometimes in these cases we don't. In fact, often we don't convert them to coulombs. But here you had to, because otherwise you're going to get microvolts. That's always what we do, is we'll just carry the times 10 to the minus 6, and we'll just carry it on into our answer. So like whenever we're dealing with microfarads, we always get microcoulombs. So that's really what we're doing. We're just carrying that prefix on. Okay? Is that clear? These are all good questions. You're going to see questions like these tomorrow. Any other particular questions? Oh, 27? Yeah. We didn't really talk about diodes at all. So we won't see diodes on here. All right? Yeah, Rachel. Oh, yeah. Okay, let's take a look. Are they on the circuits thing that the practice? Okay. Any number in your mind? 23 through 25. I don't remember. I'm pretty sure that there are some problems like these. Number 22 as well. Yeah, okay, so what happens to the voltage across R1 when the switch is closed? So the important thing is here, what happens when this switch is closed? That means that I'm adding that resistor. And so the equivalent resistance of those two resistors is going to decrease. Because when I add resistors in parallel, that causes the overall resistance to decrease. Because V equals IR, when the equivalent resistance decreases, so does the voltage. And that means that the voltage over here has to go up. If this is V1 and this is V2, because V1 plus V2, they have to equal to V, and V stays constant. So if V2 goes down, then V1 has to go up to still add up to equal to the overall voltage. So in these, you want to ask yourself, what happens to my resistance when I add or take away these resistors? Let's look at some others. Okay, well, this is a similar thing, a very similar question. So if I add this resistor, again, the equivalent of this is going to decrease, and so the voltage is also going to decrease. And just like over there, V1 is going to increase, and that means that the current, well, what does the current do if the voltage increases? It's going to increase as well, because V is equal to IR, for R1 that is. V1 is going up, that means I has to go up too. You're giving more energy to this resistor, and so you're going to get more current across it. 27? Okay. This is a power question, and so we want to remember our expressions for power. We had several. P is equal to VI. That's sort of the one we use the most. But then also we had these alternate expressions, V squared over R and I squared R. Those are on your equation sheet. But I have 10 volts on light bulb A. And then on B and C, what are my voltages? You don't know? 5 and 5, right, 5 and 5 volts. Because when I'm in parallel, this branch is parallel to that branch. I have 10 volts across each branch. So I have 10 volts across this whole thing, and then I also have 10 volts across this whole thing. But because those resistors, those two light bulbs are identical, they're going to split that 10 volts up evenly. They'll each take on 5 volts. So the point is here that bulb C has half the voltage of bulb A. Bulb C has half the voltage of bulb A. And if I have half the voltage, looking with a constant resistance, that's where you have to be careful. I put in a factor of a half right there, and that gives me a factor of 1/4 over there. Why don't I put in a factor of half right here? Why is that not complete? Right, because your current is also going to change. Your current is not constant. If I have half the voltage over a resistor, I also have half the current. That's why we have these different expressions for power, so that we can have an expression where I have one value that's constant, like here, the resistance is constant, when V and P are changing, and so I can compare just two variables that are changing, not three variables, which is what I have with P equal VI. You know, in practice, really, these are the only two that you'll be using. And often in these type questions where you're asking about the difference in power between resistors, it's going to be this one, this V squared over R. That's on your equation sheet, but it's helpful just to internalize that, think about it. Yeah, I'm sorry. I was answering how is C compared to A, but really I want to know how is A compared to C. And A, if C is 1/4 as bright as A, that means A is 4 times as bright as C. You see where I was answering a different question than what it asked. But I always start, when I run these problems, I always start with, well, what's sort of the right direction? And so on this, I wouldn't even think about the numbers yet. I would just say, was A brighter or dimmer than C? And since I know it has more voltage, then I know that it's brighter. So I would get rid of A and B and E. And so I know that I'm left with either C or D. And then I would begin to think about, okay, by what amount is it dimmer or brighter? It's a good practice to get rid of those answers that you know are not reasonable right off for various reasons that they're not reasonable. All right, what else, folks? Yeah. On this? Oh, yeah, okay. So how does, we did this one in class the other day. I have this current that comes through, and it splits up. And remember, the current is going to always, more current will go into a path with less resistance. So the one that has the least resistance is going to be the one that gets the most current. But in this case, both of these, they have the same amount of resistance. So they each get the same amount of current. But then that current comes back together. And then over here, I have two paths that are not the same resistance. So which, the top or the bottom, is going to get more current? Well, which has more resistance, the top or the bottom? The top has more resistance. It has twice the resistance. So it's going to get less current. Oh, so that's the answer. These two get the least current of all. So C is the right answer. They get the same current because they're in series. Resistors in series have the same current. And so R3 and R4 will have exactly the same current, which happens to be the least amount of current. By how much is it less than, say, R5? By how much? By what factor? If R5, say, has 8 amps, what is R3 and R4 going to have? It's going to have 4 amps. Because it has twice as much resistance, it'll have half the current. Yeah, Rachel. 100 on this? We had 100 questions on this? Have y'all done them all? Oh, some of these are multi-loops. You're not doing the multi-loop, of course. Those will not be on the test. Oh. Okay, so first thing you want to ask is, what is the voltage drop across this 482 milliamp, or across this 24 ohm resistor? The voltage is IR, which is 4.482 times 24. And that is 11.6 volts. Look, I got 12 volts for my battery. Like, that's the ideal EMF. That's my E value. And so this is my terminal voltage. That's the actual voltage that I get across this battery. So I have, oh gosh, is this going to work out right? I think it will. So I have 11.6 should equal to E minus I times R. And I want to solve that for R. Actually, let me go ahead and erase this. I'll go and put in my current, which is 0.482 times R. This E is 12 volts. And then I solve that for R. So I get 0.4 divided by 0.482. 0.8, 0.9. B was the answer on that one, 103? Yeah. I don't like that problem. It's actually not exactly correct because it's not including the potential drop across the resistor. It would be more like ones that I've given you, where I give you the terminal voltage outright. Okay? There was one like 103? Yeah. More like, yeah, more like 107, right? I mean, this one you're looking for the terminal voltage, but I have my terminal voltage is my EMF. That's sort of the ideal battery minus the voltage drop across that internal resistance. And so I have, I'm looking for the terminal voltage, so it's 20 volts minus the current, which is 5 amps times 2 ohms. That's a big internal resistance, because you should be getting 20 volts, but you're really only getting 10 volts out of this thing. Okay, does that help? Yeah. 108. People don't like these problems where you don't actually provide the picture, but you have to draw the picture or think about the picture. But you'll probably see one like this tomorrow where I just describe the circuit in words, and you have, it's not going to be a complicated circuit, it has to be series or parallel. But make sure that you can do it. And this is also a combination of our power and our circuit problems. I have a 50 and 100 ohm resistor. You don't have to draw the picture. It always helps me. 50 and 100 ohm across 150 volt. You probably know what the voltages are across those resistors. But if not, let me draw it. I have a 150 volt battery with a 150 ohm resistor. This is 1 amp then. I is V over R. 150 over 150. 1 amp across 50 ohms is going to be 50 volts. 1 amp across 100 ohms is going to be 100 volts. And then if I want to know, let's see, how can I do this? If I want to know the power across the 50 ohm resistor, I could do it in a couple of ways. I could say power is V squared over R, or I could say just power is V times I. Because I know the voltage, it's 50 volts. And I know the current, it's 1 amp. So the power is 50 watts. But then I want to know the energy. And energy is power times time. Remember, power is a joule per second, or an energy per unit time. And so it's going to be 50 watts times 3 seconds, which is 150 joules. It's a good question. I said you'll have to deal with power and figure out what is the power dissipated across a resistor. And then you'll also give you at least one problem where I just described the circuit in words, kind of like this. I might not ask the power, but I'll ask the current or the voltage or whatever. What else? About capacitor circuits, how y'all feeling on capacitors? It's been a while since we've done capacitors in class. Y'all want to do a combination circuit in capacitors? Yeah? Let's do it. What's your question? Good question. So parallel circuits give off more light because if I have two resistors in parallel, say they're identical, across a 10 volt battery, I get 10 volts across each of those resistors. But if I have those same two resistors in series, I don't get 10 volts across each. I get 5 volts across each. So the answer is because resistors in series, they share voltages. They don't take the same voltage. Now the difference here is that I got a heck of a lot more current. This current is big, and this current is relatively small. I have a bigger current through the parallel circuit. I'm making more energy, right? Giving off more light, so I have to have more current. All right. Yeah. Yeah, probably. You want to do this one? Yeah, if it really freaks you out, add some values to it. But it's easier if you don't, because you might add values that make it a little bit difficult. You understand?
I did it, and I added 2 to 1, 2, and 3, but I got 4. I mean, I got 8, and the answer is 4.
Okay, I'll do it with numbers, I'll do it without. But let me do it without first, because that's the easier way. So I have my capacitors. This one is C, and this one is 2C, right? Because when they're in parallel, they add up, capacitors. And then this is 12 volts. Now, We've done this before, where if I have two capacitors that are different by a factor of 2, what is their voltage? Especially with 12, right? Because I know that 8 plus 4 equals 12, and I also know that 8 is twice 4. I know that my voltages here are going to be 8 and 4. And then I just need to make sure I assign them correctly. So my 8 volt, the big voltage will go to the big or small capacitor. The small one, right? So capacitors that are small have big voltages. Capacitors that are big have small voltages. So that's 8 volts, and then this is 4 volts. Let me remind you of why that is. So Q is equal to CV. For capacitors in series, Q is constant. And so if C gets big, V gets small. Now this is different for resistors. It's the opposite for resistors. Because for resistors, I is constant. And so if R gets big, V gets big. It's an inverse relationship with capacitance and voltage, or with charge and voltage, capacitance and voltage for capacitors, but it's a direct relationship for resistors. More resistance, more voltage. More capacitance, less voltage. You get more charge. Actually, no, you don't. Less voltage. Okay? Let's put numbers in. You said you used 2? All right, so that's fine. So that would give us a 4 microfarad and a 2 microfarad. 12 volts. What did you get? I bet I know what you did. So define the equivalent here. A 1.3. 1/2 plus 1/4. That's 2/4 plus a 1/4. Yeah, that's 1.3. 4/3. So that's the equivalent, is 4/3. And then the charge on that equivalent capacitance, 12 volts. Q is equal to CV, 16 microcoulombs. Is that right? Yeah. So I have 16 microcoulombs here and 16 microcoulombs here. And then if I want to know the voltage, it's Q divided by C. 16 divided by 2 is 8. 16 divided by 4 is 4. What did you do? Okay. Yeah, so because we were looking for the voltage across C3. You can do numbers, but look, it's a lot more difficult to do numbers. It takes more time. But if the variables freak out, it's fine. I'm okay with you doing numbers. It's just you might get like you might make a mistake along the way. Now what else? Oh, you want to do a like a series? You want to do 23 and 4? Okay. All right. Do y'all have your packets? I know a lot of y'all have come to the help sessions. Are there some that I haven't done? If you have one from that help session. Yeah. Well, let's do 32. We might have done the equivalent, but then also let's ask, what is the voltage? Oh, shoot. Y'all can probably tell me. You might not be able to tell me. Let's look at them. Let's say I want to know the voltage across this 1 microfarad. What's the voltage across that 1 microfarad? Well, anytime I encounter a circuit like this, I just want to start simplifying it. Even if I have no idea what to do, just start simplifying it and make a few steps in the right direction. And then usually the answer will become more apparent. So I'm going to simplify this circuit by combining the 1 and 5. Those are in parallel. And then also the 8 and 4. Those are also in parallel. 1 plus 5 is 6 microfarads. 8 plus 4 is 12 microfarads. 24. So, well, what are two numbers added together, add up to 24, but one's twice the other? 8 and 16. 8 and 16. So I know that I have 16 volts here and 8 volts here. I know that I have two voltages, one twice the other, that have to add up to equal to 24. Right? So then I say, what are those two voltages? Well, it has to be 16 and 8. Those are the only two numbers that add up to 24, where one is twice the other. You assign the bigger voltage to the smaller capacitor. Okay? Those are helpful hints. They will make your test go from an hour-long test to be a 30-minute test, if you can see those little hints along the way. Okay, so if that's 16 volts, then that's also the answer here. That's 16 volts, that's 16 volts, this is 8 volts, and this is 8 volts. Okay? What else? Look, 33 is like you have two capacitors that are split by a factor of 2, but it's not so obvious what the charge is or what the voltages are, just because you can't split up 10 evenly like that. Like, there's no even number that, you know, like 8 plus 4 is 12. There's nothing for 10 like that. So what I have to do here is I say 1 over 2 plus 1 over 4. That's 4/3, 1.3. That's my equivalent. My charge on the equivalent is 4/3 times 10 volts. That's 13.3 microcoulombs. And then realize that capacitors in series have the same charge. And so if I have a capacitor that has 13.3 microcoulombs on it, that's the equivalent, then both of these will have 13.3 microcoulombs. Capacitors share voltages. They split them up between them, but they have the same charge. It's kind of like resistors in series having the same current. It's a very similar thing, like an analogy. It's not the same physically, but the rule works out a lot the same as for capacitors in series have the same charge. Resistors in series have the same current. I remember that because, you know, charge, current, they're related. They're a lot alike. So you will encounter some circuits where the numbers just aren't easy, that you actually have to go through this process for these capacitors or resistors in series. All right, what would you like to look at? Look at some other old tests? Yeah? Okay. Let's look at, we'll go back to spring 13. Well, let's do this one. What's the equivalent resistance of this circuit? Well, a 2 and a 2 in parallel, that's equal to 1 over a half plus a half, and then a 1, so I can replace this guy with a 1 ohm resistor, and then the 1 and the 4 I can replace with a 5 ohm resistor, and then so to find the equivalent, I would say 1 over 5 plus 1 over 5. That's 2/5 or 5 halves. 1 over 2/5, which is 5 halves, are 2.5 ohms. So C is the right answer. But here, what if I wanted to find the voltage across the 4 ohm resistor? Well, we're saying that this is 10 volts. I wanted to find the voltage across the 4 ohm resistor. Let me draw this circuit. I have a 1 and a 4 ohm resistor. 1 ohm, 4 ohm. Right, I took this 1 ohm and redrawing it there. And then I imagine that it's like it's connected up to its own 10-volt battery. In parallel, that very much is what you have. That it's like that parallel branch is hooked up to its very own battery. Because remember, branches in parallel circuits are completely independent of one another. They don't affect one another. So here, if I want to know the voltage across the 4 ohm resistor, I would first find the equivalent, which I know is 5 for that little branch. And then I find the current. The current here is 10 volts divided by 5 ohms, which is 2 amps. So I know I have 2 amps here and 2 amps here. So the voltage across this resistor is 8 volts. No multi-loop circuits at all, no household circuits, no junction rule. What happens to the potential across R1 for this one? If I close that switch S, go up, down, stay the same, goes up, right? So, is that what you said? So if I close this switch, this equivalent goes down. That means the voltage across this part also goes down. And so that means this voltage has to go up, because the sum of the voltage has to equal the voltage of the battery. Well, this was an easy test. They're not easy if you don't know how to do it, though, right? So you need lots of practice. And even if you do know how to do it, but you just haven't practiced enough, you get on there, and man, all those symbols, they just start all looking the same. Like, they're confounding if you haven't practiced. But if you've practiced, then you'll begin to see patterns, and you'll just become more familiar with the circuits. It'll be all right. Okay, let's look at spring 14, I guess. Well, that's this one. Let's look at spring 12. Anything stand out to you? Do another circuit problem. Y'all know how to do this one? What's the current in the 3 ohm resistor for this? And then further, what's the overall current? Current in the 3 ohm resistor? It should be a quick one. Like when you encounter a parallel circuit, it should be quick, quick, quick. 6, right. So each of these have 18 volts on them. And so if I have 18 volts across 3 ohms, the current is going to be 6 amps. 6 amps. Because I know that I have 18 volts here, and I have 18 volts here. And I is V over R, or that's 6 amps. What's this current? Well, I know I have 6 amps in the top branch. What do I have in the bottom branch? I have 3 amps in the bottom branch, 18 over 6. And so that means that this current, the total current, has to be 9 amps. That's our junction rule. So if I have 6 amps here, 3 amps here, going into that junction, I have to have 6 plus 3 amps. We see the junction rule in multi-loop circuits, but we've been using it for a month now, so a couple of weeks anyway. That's all magnetic fields. Let's see, 15. Y'all look excited to be here. Any questions on this one?
Yeah.
Number 12. Okay, so number 12 it's one that we've done before. Likely you might see it tomorrow. I'm not sure. I don't remember honestly. But often I put these questions on there just to make sure that you know how to calculate resistivity and resistance. So here the idea is that I can choose materials based on their resistivity, which I can measure fairly simply. R is equal to rho L over A. And so rho is equal to RA over L. Just multiplying each side by A and dividing each side by L. And then I can calculate what the resistivity should be. I also need to find the resistance. R is V over I. That is 1.4 over 20. What's that, 0.07 ohms? That's right, huh? Yeah. So I have 0.07 ohms. The area is given. It's the 7.85 times 10 to the minus 7. Divided by the length. The length is 1 meter. .5 times 10 to the minus 8. That's tungsten. So the answer is D. Yeah. Okay, so on these, we saw these in the concept test, and there are sort of a couple steps that you have to go through. First of all, ask yourself, what is happening to the capacitor? So the capacitor is equal to kappa epsilon naught A over D. It's the first step. The capacitance here, the distance is being doubled. So this is twice the original value. That means that my capacitance is decreasing by a factor of a half. So my capacitance is decreasing. Then ask yourself, is the charge remaining constant or is the voltage remaining constant? And in this case, if they're disconnected, that means I have constant charge. I connect the capacitor to a battery, I put charges on it, and then I take it away. That charge is always going to be the same. I can't put new charges on it or take charges away. And so I have constant charge. Q is equal to CV. By changing the capacitance, since this is constant, I'm doubling the voltage. And so whereas the voltage was 200, now it's going to be 400. Now, if I left it connected to the battery, you would have a different situation, because in this case the charge can change, but the voltage remains constant. And so I'd have Q equals CV. My capacitance decreases by a factor of a half. My voltage remains constant, so my charge would decrease by a factor of a half. So two questions you want to ask yourself. First, what happens to the capacitor? How does the capacitance of this capacitor change when you change the dimensions of it? And then the second thing you want to do is ask yourself, what's remaining constant? Is the charge or is the voltage remaining constant? The charge is remaining constant if it's disconnected from the battery. I charge it on the battery, I take it off, and that's all the charge I got. But the voltage remains constant if it stays connected to the battery. The charge can change, but the voltage stays the same. Okay? Yeah, don't try to memorize them because there are lots of different iterations on this as you change the various dimensions of the capacitor. Just remember those simple rules about what happens to the capacitance and then what remains constant. Yeah. You'll probably have one like number 2, where you just have to calculate the capacitance. So here, C is equal to kappa epsilon naught A over D. And you had at least one on OpenStats for like number 2. Really, it's just knowing what the variables represent. So kappa is the dielectric constant. Epsilon naught, that's on your equation sheet, the permittivity of free space. 8.85 times 10 to the minus 12. It's in farads per meter. And then A is 0.2. And then D is 1.2 microns, or 1.2 times 10 to the minus 6 meters. And then whatever that capacitance is, 7.4 microfarads, that's what I got. 7.4 times 10 to the minus 6 farads. So E is the right answer. You'll have one of those. Make that an easy one, okay? Likewise with the resistivity. I just want you to know how to calculate where you have the table with all the different metals. I just want you to know what the variables are and just show that you can calculate them. Make that one a gimme, okay? That's a gimme? So you know your rules. Oh, this is voltmeters and ammeters. Yeah, make sure you know that. But also make sure you know your in series and parallel rules for resistors and capacitors. Let's see if there's a similar one here. Oh yeah, like number 16. For which of these rules is not correct? Number 2 is not correct. Just number 2. All the others are correct. Okay? Yeah. Okay, so the resistance doesn't depend upon the current. If you have an ohmic device, the resistance does not change when the voltage or the current changes. That's what ohmic is. Instead, the resistance is dependent upon rho, L, and A. This is A, the radius, right? The bigger the radius, the bigger the area. This is also A, this is rho, and then this is the length L. So it's dependent upon all of those things, but it's not dependent upon the current. Now some devices, or if you put too much current in some devices, then they will no longer be ohmic. That means that their resistance will change. But that's when they're being used improperly or when they're not ohmic devices, like a diode is a non-ohmic device. Okay? What test is this? This is a good test. I like this test. I just give you this one. No, I give you a new test. You have a brand new test. Don't worry. But this is good practice for you. 21. You know how to do 21? It looks funky, right? Because you got that 1 ohm resistor on the side, and it's sort of all compact. But really, it's like ones that we've done. My 2 ohm. There's my 1 and my 2 ohm. And then there's my 6 ohm. 2, 1, 2, 6. And then so to find the current through the 1 ohm resistor, well, you might be able to do it without drawing stuff out. This is a 6 and a 3, which is what in parallel? That's 2. So then I have 2 and 2 in series. So what's going to be the voltage here? These two are 2 ohm, or this equivalent is 2 ohms. So I have a 2 ohm and a 2 ohm in series. And so the equivalent with 12, or the voltage across each of these is going to be 6 volts here, and then 6 volts across this whole thing. I'm going to have 6 volts here, and then my voltages are going to split up here. Which one's going to have the bigger voltage? The 1 or the 2 ohm resistor? The 2 ohm resistor. And it's going to have a voltage that's twice as big as the 1 ohm resistor, or 2 volt, 4 and 2 volts. They have to add up to equal to 6. So my voltages look like this. Now, you might not be able to do it that way, and that's okay. But if you can't do it that way, make sure that you can go back and figure out the equivalent resistances along the way. You have to figure out then the currents through this branch, because I know I got 6 volts across 3 ohms, so that's 2 amps. 2 amps across 1 ohm is 2 volts. 2 amps across 2 ohms is 4 volts. Rachel. That's right. And often, usually when I have those, the resistors are off by a factor of 2. And so you want to think of what are the voltages that add up. So the total, but are different by a factor of 2. All right, we've seen 16. What is that? That was, or did we do 16? There's 24 volts, that's 8 and 16. 12 volts, that's 8 and 4. 6 volts, that's 2 and 4. Alrighty? How y'all feeling about the exam? How was stats today? Y'all did it today? Did it statistics? Anybody? Nobody? Other exams tomorrow? Organic or whatever? No? This sucks, right? Yeah, I like that. Any other questions?
Is it true you have a big resistor, you have a big voltage, so the small capacitor, that's a big.
That's right. Big resistor, big voltage. Small capacitor, big voltage.